Hi there, welcome to my channel. In this video, I'm going to discuss about the solution for cloning a graph. Let's look at the problem description. We are given a reference of a node in a connected undirected graph and we have to return a deep copy of that graph. Okay. Each node of that graph has a value and also it has a list of neighbors. And the graph is represented as an adjacency list wherein each entry contains the list of neighbors of that node. And also this adjacency list is a one indexed list, meaning the first entry is the neighbors of the node with value 1. The second entry is the neighbors of the node with value 2. Third entry is the neighbors of the node with the value 3. The fourth entry is the neighbors of node 4. So if we have to clone each node in the graph and connect them as it is connected in the original graph and then return the starting node of the cloned set. Okay. So in the case of example 2, the adjacency list has only one entry. That means it has only one node and it doesn't have any neighbors. So the adjacency list of the output graph is also an array with a single entry. In the case of example 3, the input graph is empty, so the output graph is also should be empty. Okay. The constraints for this problem are the number of nodes in the graph is in the range from 0 to 100 and the node value is ranging from 1 to 100 and the node values are unique for each node. There is no node with the duplicate values. And also there are no repeated edges and no self loops in the graph. Self loop means the node point to itself. Okay. And also the graph is connected and all the nodes can be visited starting from the given node. So the single traversal should be enough to visit all the nodes in the graph. Let's look at the approach to solve this problem. So the input graph is represented as a list of edges here and edge list representation of the expected output is also same. Okay. As per the problem constraints, this graph is connected graph. We can visit all the nodes in a single traversal. To do the deep copy of this graph, we can do a breadth first traversal and also we need to use a map which will keep track of what nodes are cloned so far. Okay. So basically we do a breadth first traversal on this graph. As we traverse each node, we clone that node and then add it to the map data structure. Okay. So the map data structure's key value will be the value of the node and the value of that entry will be pointer to the cloned node. This is the information we have to store. When we do a breadth first traversal of this graph, the breadth first traversal tree will be look like this. Where when we start the traversal from node 1, so that will become a root of the breadth first traversal tree. Next we visit the neighbor of node 1 which is 2 and 4. So first we visit 2 and then 4. Next we visit the neighbors of node 2. So in this case node 3 is the neighbor which is not yet visited. Node 1 also a neighbor of node 2 but it is already visited. So we will skip processing that. So as we traverse, we have to update the cloned graph map. The visited map is used for doing that breadth first traversal to keep track of which node is visited. The cloned graph map is used for storing the cloned node. Okay. For example, when we traverse this node, we clone that and add an entry in this map. And then when we traverse the children of this node 1, we check whether there is an entry in the cloned graph. If there is no entry, then we cloned those nodes but without populating the neighbor list. Same way when we traverse node 4, we add an entry here. Okay. We yet to visit the node 3. Okay. Because the node 2 and 4 are visited, we have to update the neighbor list of node 1. Okay. So basically we populate the neighbor list in the cloned graph only if those neighbors are cloned. Okay, until then it will have only the value with the empty neighbor list. We repeat this until we visit all the nodes in the graph. That's what I have written here. So basically we do the breadth first search on the input graph and clone the nodes as they are visited. Okay. First we initialize the cloned graph map and then the first node. So this first node is used for locating the first node in the cloned graph. Okay. So whenever we visit a node, we'll have to check whether there is an entry for that node in the cloned graph. If there is no entry, then we clone that node and add the new node in the cloned graph map. Okay. And also if the node if the first node is null, that means the node which is cloned right now is the first node in the new graph. So we update the first node if it is null. Okay. Next we traverse the neighbors of the current node, and for each neighbor, if the current neighbor is not present in the cloned graph, then we clone that neighbor node and add an entry here, as well as add that new node into the list of neighbors of the current node. We repeat this until we visit all the nodes in the graph. Let's look at the flowchart. Input for this procedure is a start node and the visited map. Okay. First we initialize the queue, which keep track of the next node to be visited, and cloned graph map, which is for storing the cloned nodes, and then the new graph start will be initialized to null. First we add the start node to the queue and then mark that start node as visited. Then we enter this for loop. This will run as long as there is an element in the queue. Okay. So if the queue is not empty, then we dequeue the element from the queue and check whether there is an entry in the cloned graph map. If there is no entry, then we clone the current node and add an entry to the cloned graph map. Okay. And then we check whether the new graph start is null. That means the node which is just cloned is the first node in the new graph. So we update the new graph start variable with the pointer to that new node. Next we get the list of neighbors of the dequeued node. Then we enter this for loop, inner for loop, to process all the neighbors of the current node. Each iteration we check whether the neighbor is visited already. If the neighbor is not visited, then we mark that node as visited and add that to the queue. And then we check whether there is an entry for that current neighbor in the cloned graph. If there is no entry, then we clone the current neighbor and add an entry to the cloned graph map. And then we add the new node to the neighbors list of cloned current node. Okay. And we repeat this until we process all the neighbors of the current node. Once all the neighbors are processed, then we come out and process the next element in the queue. Once the queue is empty, then we come out of this outer loop, and then we finally return the new graph start, which points to the first node of the cloned graph. Let's move on to coding. First I initialize the visited map, which is of type map of int to pointer to node. Next I check whether the input node is null. If it is null, then I return null. Otherwise, I call BFS function to traverse this graph and assign the return value to new graph variable. So the BFS function takes the pointer to starting node and then the address of visited map. Then I finally return the new graph. Next I write the BFS function. First I initialize the cloned graph start and cloned current and cloned neighbor pointers to null. Next I initialize the boolean OK to false. Then I initialize the cloned graph map, which is of type map of int to pointer to node. Then I initialize the queue with the start node. Then I mark that current node as the visited by adding an entry in the visited map. Next I write the for loop. This will run as long as there is an element in the queue. Each iteration I dequeue the first element in the queue and assign that to current pointer and then update the queue. Next I check whether there is an entry for the current node in the cloned graph map. If there is no entry, then I clone the current node. So the new node is initialized with only the value with the empty neighbors list. This will be populated as we traverse the neighbor of the current node. Next I add the new node into the cloned graph map. Basically I add an entry for that node. Next I check whether the cloned graph start is null. That means we are processing the very first node in the graph. So the cloned node will be assigned to this pointer. Next I get the neighbors list of the current node and assign that to neighbors variable. Then I write the for loop to process all the neighbors. Each iteration I check whether that neighbor is already visited. If it is not visited, then I mark that node as visited by adding an entry in the visited map and then I add that node to the queue. Next I check whether there is an entry for that neighbor in the cloned graph map. If there is no entry, then I clone that neighbor and add an entry into this cloned graph map. So whenever a node is cloned, only the value is initialized and the neighbor list is left empty. Then that new cloned node will be added into the cloned graph map. Next, the cloned neighbor will be added to the neighbor list of the cloned current node, which is cloned in the outer loop. Then finally I return the cloned graph start pointer, which is pointing to the first node in the cloned graph. Next I am going to run the test cases. All the tests passed. Next I am going to submit this program. Cool, this program is accepted. Next I am going to do the code walkthrough with sample input. This adjacency list represents the input graph and this list represents the output graph. Okay. First we initialize the visited map, which is a map of int to a pointer to a node, and then we check whether the node is null. If it is null, we return without doing a breadth first traversal. Okay. Otherwise we call the BFS function to do the breadth first traversal. Okay. So first we initialize the cloned graph start and cloned current and cloned neighbor node pointers to null. And then we initialize the cloned graph map, which is a map of int to a pointer to a node, that is also initialized with empty map. Next we initialize the queue with the starting node for this traversal, okay, and mark that node as visited by adding an entry in the visited map. Okay, so we have an entry for node 1. Next we enter this for loop, outer for loop. This will run as long as there is an element in the queue. Okay, so now there is one element in the queue, so we enter the for loop. In the iteration 0, we dequeue the first element in the queue and the current is 1 and the queue will be empty. Okay, and then we check whether there is an entry for the current node in the cloned graph. Right now there is no entry, so we cloned the current node and add an entry in the cloned graph. Okay, so here if you look at it, we are not updating the neighbors list, only the value is initialized. This will be populated as we traverse the neighbors of the current node. Okay, so right now the node value is there and we have added an entry. Then we check whether the cloned graph start is null. In this case it is null, so we initialize that with the current node. Okay, so the cloned graph start is pointing to node 1, that is in the cloned graph. Next we get the neighbors list of the current node. The node 1's neighbor list has node 2 and 4. Okay, so this inner loop traverses this list, and in iteration 0 we have neighbor 2 and we check whether that neighbor is visited already or not. So in this case it is not yet visited, so we add an entry for that node. Okay, and then next we check whether there is an entry for that neighbor in the cloned graph. There is no entry for node 2, so we cloned that node and add an entry in the cloned graph. Same for the node 4, we add an entry for the node 4 in the visited map and add cloned that node in the cloned graph map. Okay, and one more you can notice here, so when we process this neighbor, we add that cloned node in the neighbor list of node 1 in the cloned graph. So here you see that is empty, but when we process the neighbor 2, that gets added in the cloned graph. Similarly, if you see here, the node 4 is added. Okay, so the neighbors list will be updated in the cloned node as we traverse the neighbors of that node. Okay, then now when we leave the inner loop, we have node 2 and 4 in the queue. Okay, so when we come out, we dequeue the node 2 and then we check whether there is an entry for that node in the cloned graph. It is already there. And also we check whether the cloned graph start is null. In this case it is not null, so we are not doing anything here. Next we get the neighbors list of node 2. So node 2's neighbor list is 1, 3. Okay, then we enter the inner loop to process node 1 and 3. Okay, so in the iteration 0, we check whether there is an entry for node 1, whether the node 1 is already visited or not. So in this case it is already visited because there is an entry for that node in the visited map. So we are not adding that to the queue. And also we check whether there is an entry for that node in the cloned graph. There is an entry, we are not cloning that node 1. But now we have to append the current node to the neighbors list of the cloned current node. So in this case the node 1 should be added to the neighbor list of node 2 because we are processing in the outer loop. No, we are processing the node 2 in the outer loop. So we have to add this node's cloned version as a neighbor of node 2. That's what we are doing here. Similarly, when we process the neighbor 3, we check whether there is whether that node is already visited. In this case it is not yet visited, so we add an entry for node 3 and then we add node 3 to the queue. Okay, after that we add the cloned version of that node 3 to the neighbor of node 2 in the cloned graph. That's what we are doing here. Once node 1 and 3 are processed, then we come out and dequeue the node 4 from the queue, whether there is an entry for that node in the cloned graph. there is an entry already there. In that case, we do not have to clone that node this time. Next, we get the neighbors list. Neighbors list of node 4 has 1, 3. Okay. So we process node 1 and 3 in the inner loop. Okay. So we check whether the node 1 is already cloned, because there is already an entry in the cloned graph. We are not doing anything, but we add node 1 as the neighbor of node 4 in the cloned graph. So that's what we are doing here. Next, we process the neighbor 3, and there is an entry for that in the cloned graph already. So we are not cloning node 3 this time, but we have to add node 3 as a neighbor of node 4 in the cloned graph. That's what we are updating here. So here we add only 1 here. Next we add node 3 as a neighbor. When we come out of this inner loop, we have only one node in the queue, which is 3. So now we go ahead and process the node 3 by dequeuing that from the queue, and then we get the neighbors list, which has node 2 and 4. Okay, and because node 3 is already cloned, there is an entry for that. We are not cloning that node, but while we are processing its neighbors, we add those neighbor nodes to the neighbor list of node 3. Okay, so in the iteration 0, we process the neighbor 2, and then that neighbor is added to the neighbor list of node 3 in the cloned graph. Similarly, node 4 is added to the neighbor list of node 3 in the cloned graph. So finally we have 2, 4, 1, 3, 2, 4, 1, 3 as the adjacency list. That is an expected output. Next, I'm going to do the time and space complexity analysis for this solution. Time complexity of this procedure is order of n, where n is the number of nodes in the graph. Okay. So in order to clone this graph, we have to traverse all the nodes in the graph, and the BFS traversal ensures that nodes are visited only once. For this case, there are 4 nodes, so we visited 4 nodes in the BFS traversal. If there are n nodes, then the BFS traversal will visit all the n nodes once. So the time complexity is order of n. Space complexity is also order of n, because we need to allocate space for each node in the graph to store it in the visited map, and as well as the cloned graph map. Okay, if there are n nodes in the graph, then we need n entries in those two map. So the space complexity is order of n. Thanks for watching this video. Have a great day.